Hi. Now suppose we take a curve and we look at an area bounded by the curve, the x-axis and two vertical lines. Now if we take this area and spin it about the x-axis, we generate what is called a solid of revolution. And in this tutorial what I'm going to show you is how we can find the volume of such a solid. And also in a later tutorial what I want to do is extend this work to taking an area trapped between two curves and now revolve it around the x-axis. You'll notice we generate this solid of revolution, kind of like a funnel with this hollow in it, okay? And in these tutorials we find volumes like this by using integration methods. Now suppose we have a finite region bounded by the curve y equals f of x, the x-axis and the lines x equals x1 and x equals x2. And if we rotate this region about the x-axis through 360 degrees or the equivalent of 2 pi radians, then what we generate is this solid of revolution. And if we want to find the volume of this solid of revolution, it can be shown that it's equal to pi times the integral of y squared with respect to x, going between the limits x1 to x2. So we've got our limits there, x1 to x2. Now I'm giving you this formula here without any proof. But in a later video what I'll do is I'll show you how it is derived. But for now all I want to do is just show you how we can use it. So we've got an example here. I've got the curve y equals x squared plus 1 and we have this region here bounded by the lines x equals 1 and x equals 3 and the x-axis. And if we rotate this through 2 pi radians or 360 degrees about the x-axis, we generate this solid of revolution. And if we're going to find out the volume of this, we'll call it the volume V. Then according to this equation up here, that volume V is going to equal pi times the integral of y squared, or y is x squared plus 1, so if we square that we've got x squared plus 1 all squared integrated with respect to x, going between the limits x is 1 to 3, so we're going from 1 to 3. So in the usual way what we would need to do is expand the brackets, so we've got the integral from 1 to 3 of, and expanding the brackets gives us x to the power 4 plus 2x squared plus 1, and we're integrating that then all with respect to x. And integrating this gives us, well, x to the power 5 over 5 for that first term. Integrate the 2x squared with respect to x and we get 2x cubed over 3. And finally integrating 1 with respect to x just gives us x, and that's going between the limits then 1 to 3. And if we substitute our limits in, we've got, for the first one, when we put the 3 through, we've got 3 to the power 5 divided by 5, and then plus 2 times 3 cubed all over 3, and then plus 3. And then for that we now subtract what we get when we put 1 through, so you're going to get a fifth for that first term, and then for this term that will be 2/3, and then for the last term here it'll be plus 1. Now if you use your calculator to work this out in terms of pi, what you get is 1016 over 15 pi. And because it's a volume, I like to write units cubed. Not that you necessarily have to write that. I doubt whether you're going to lose any marks in an exam, but as I say, being a volume, I would always do something like that. Now you're going to need to do more examples to get practice on this, but I hope for now that this has given you a brief introduction on what we mean by a solid of revolution and how we work out the volume of that solid of revolution when it's spun about the x-axis. It's given by this formula. Now in later tutorials what we'll do is extend this idea, and also I'll show you how we derive this formula.